Yes, go ahead.
Okay, so let's refine the type, and let's do it in the dependent ML style. So let's refine the type natlist, which is just the type of list specialized to natural numbers. Let's give it the sum of the elements refinement by giving it an index, and let's say that the empty list sums up to 0, and that a con cell sums up to n plus m, where n is the head element and m is the sum of the tail list. Okay, say we want to add another refinement, this time the length refinement. So we add another index representing the length, follow the same pattern. We'll say the empty list has length 0, and that a con cell has length 1 more than the tail list. The point I want to get across here is if we continue this process, if we want to add more and more refinements, it gets unwieldy pretty quickly. Seems we can do a bit better by using measures, which were introduced in liquid types. So for example, we can define the sum measure, which is just a small functional program, and then use that measure to refine our data type by using like a set builder kind of notation. And then we can use this refinement type to refine our usual functions. So this is the usual append function, but we can give it a refinement type saying that if you append a list that sums up to n1 to a list that sums up to n2, then you'll get back a list that sums up to n1 plus n2. Okay, if we want to add more measures, refine this type by more measures, we can define another measure, say the length measure, and then use that in our refinement type, and then use the refinement type as usual. Okay, perhaps this seems a bit better, but it's actually pretty hard to implement fancy types like this. So the first liquid types paper had a strict evaluation order, and at least at first it didn't have a soundness proof. And then later, Haskell was refined to have liquid types, but Haskell has a lazy evaluation order, and this was part of the reason why they found that the implementation was unsound in practice. So they came up with some restrictions on let binding and subtyping to recover soundness. And this isn't unique to liquid Haskell. So historically, like the combination of fancy types and standard ML led to unsoundness in implementations that had to be patched to recover soundness. Okay, so like the point of this paper is to fit a foundational type system of measures in one paper. And so we think such a paper ideally should have at least the following. One, a declarative specification together with proofs of its correctness. Secondly, an algorithm for the specification together with proofs of its correctness. But this is a tough nut to crack. Here's roughly how we soften the shell in the paper. First, we observe that measures are folds of algebras with SMT index sort carrier. Second, we decompose measure-refined algebraic data types logically in terms of algebraic value types, that is, sums and products, as well as SMT solvable constraints expressed in asserting and existential types. And dually, we have guarding types and universal types. Third, we use value-determined index quantification as well as an unrolling judgment. 4, we use call by push value and the proof-theoretic technique of focusing. 5th, we use bidirectional typing, let normality, and polarized subtyping. And by combining all these things, we can prove correctness. Okay, let's turn back to our append example, but this time let's consider applying it to these two arguments, the list containing 3 and the list containing 2, 0, and 0. So the typing algorithm has to be able to infer indices for M1, N1, M2, and N2. Here, these indices can be synthesized locally because they're determined by the values. In particular, this list sums up to 3, and it has a length of 1, and the second list sums up to 2, and has a length of 3. So these are the indices that get synthesized, semantically speaking. Okay, let's turn to another example, filter. So this is the usual filter function, but I give it a refinement type, which says that if you filter a list of length n by some predicate, then the list you'll get back is a list of some length m less than or equal to n, the length of the input list. Okay, and if we write this let normal program where we assign the result of applying filter to these arguments, list containing 1, 2, 3, and the predicate is what is the number greater than 2, then the algorithm has to be able to synthesize an index for n. In this case, an index semantically equal to 3 would be synthesized. However, it would not need to synthesize an index for m unless we were to run this program and get a result of a list containing 3. If you were to check this value against the existential type, then the m would be solved to an index semantically equal to 1. And we can see that that is indeed less than 3. Okay, so in our system, these value-determined indices are synthesized by the end of a focusing stage, which is always marked by a polarity shift, which in call-by-push value terms is a lift or a thunk. In the example, the upshift was implicit. So there is an implicit shift from negative types to positive types. Okay, so here's our refinement type grammar, which is basically call by push value with sums and products, as well as our refinement types, which include guarding types, universals, asserting, existential, and refined algebraic data types. And I'd like to point out here that the phi and the a and the tau and the alpha and the t, these all live in an index domain, which we keep separate from the program domain in order to ensure decidability. Okay, so we modify the usual typo formant judgment by adding an output context xi, which keeps track of the value determining positions within types. So the only time we add an entry to the output xi is when there's an index variable in this position. That is when it's the result of a measure applied to an inductive value. And we require both existential and universal quantification to quantify over the value determined indices, that is, over the output of the underlying type, the output xi of the underlying type. By doing this, we find that we can simplify the semantics and facilitate the proof of algorithmic completeness. Okay, so we have an unrolling judgment, which is basically for connecting the syntax of values to the appropriate SMT constraints. This judgment may look a bit scary, but I just want to highlight this example. So if we were to feed in the type of NAT list that sum up to n into this judgment, then it would output the following type, which basically says the nil case sums up to 0, and a con cell sums up to n, where m is the head element and n prime is the sum of the tail list. So depending on the syntax of the value, a complete algorithm has to be able to solve m and n prime depending on the syntax of the value. Like, for example, if it's a con cell. Okay, so in the algorithmic system which solves these indices, it's pretty close to the declarative system, except for a few differences. Mainly, one, whereas a declarative rule conjures an index, the corresponding algorithmic rule creates an existential variable, and then the system explicitly solves it by exploiting system invariants such as polarity. Secondly, whereas a declarative rule verifies an index proposition, the corresponding algorithmic rule delays it until all the evars appearing in the proposition are solved, which happens necessarily by the end of the focusing stage. One of the invariants that we exploit in order to solve for existential variables comes from the polarity of subtyping. In particular, we maintain the invariant that positive subtypes and negative supertypes never have unification variables, so these can be used to find solutions. Polarized subtyping has also been found helpful for type inference algorithm for generalized algebraic data types. And we use a certain kind of let normality in our system so that we can restrict subtyping in the system only to variables. Because we do this, in order to prove that typing is stable under substitution, we have to prove that general subsumption is admissible. That is, it holds not only for variables, but for any kind of program term, values or expressions, or whatever. So the syntactic substitution lemma is a key step to proving type soundness with respect to an operational semantics, which is usually formulated today in terms of progress and preservation lemmas. However, in this paper, we prove type soundness with respect to a denotational semantics, which is a fairly standard call by push value semantics, where we interpret value types as certain kinds of predomains and computation types as certain kinds of domains, but there's also some refinement stuff mixed in. For example, in order to prove that our typing judgments are sound, that is, if you have a typing judgment and an interpretation for its free variables, then the interpretation of the program is in the interpretation of the type. And in order to prove this, we have to prove that our notion of value-determined indices are sound, for example, which says that if you have a type A that is well-formed under theta and has value-determined indices xi, and if you have two different interpretations for theta, and if you have one value in both of those interpretations, then those interpretations must agree on the value-determined indices of the type. So, for example, this value, a list containing 7 and 19, determines this index n to be 2. Uniquely determines it to be 2, semantically speaking. However, the index m can be either 0 or 1, so we don't say that's value determined. We also prove that substitution soundness holds, which says that syntactic and semantic substitution commute. But if you read the paper, you'll find many more results. But to give a summary of the declarative results, so we give a polarized declarative system that has subtyping, universal and existential types, index refinements with SMT solvable constraints, and nullary recursive predicates on algebraic data. We prove that substitution holds. We provide a clear denotational semantics of the declarative system, and then prove that typing is sound with respect to it. This relies, as mentioned, on proving the soundness of our notion of value-determined indices. Typing soundness implies, relatively simply, the logical consistency and total correctness of our system, even for programs that are not structurally recursive. And total correctness includes total pattern coverage for pattern matching. We also prove that syntactic substitution is semantically sound. For our algorithmic results, we provide a polarized subtyping and typing algorithm. We prove that it's decidable. We prove that it's sound and complete. And this relies on proving that all of the existential variables are solved by the end-of-focusing stages, which is possible to do because they're value determined. Okay, so how is this supposed to help us understand Luca types? Well, at least we have a bit of empirical evidence that it does help us. In particular, there's a liquid types paper recently published called Flux, Liquid Types for Rust, where they're quoted as saying that the exact restrictions that they use to guarantee unification always succeeds are best described in the paper focusing on refinement typing, the paper I'm presenting now. Okay, so to conclude, let me summarize the paper. If you interpret measures semantically and logically, and if you apply proof theory compatibly with value determinists, then you get a correct liquid typing algorithm with a clear specification. This paper lays down much of the groundwork for a great deal of further work to be done. For example, there are syntactic simplifications to be made that obviates an extraction judgment. I didn't mention it in this talk, but you would find it if you read the paper. We would like to extend our paper to non-nullary measures and multiple measures, as well as polymorphism and refinement abstraction, and we would like to apply it in various ways. I'm personally interested in applying it so that it not only does termination checking, but checks termination within a certain time or space complexity bound. Thank you.
All right, I think we can start with a question from Discord while you get the mic to another in-person question asker. So the question on Discord is, could you add linear types in your theory to have indices over types of resources?
Maybe. I hope so, yeah, that'd be an interesting project.
All right. Do we have questions from the room?
But I don't see why not.
Thank you. That was a impressive talk. You make this nice case for using measures instead. But if I was writing in AGDA, I could index things to get vectors, or I could say all lists whose length is right. There exists a list such that its length is equal to such and so. I could do it either way. In AGDA, I think I'd be advised to do it in the indexed way because the proofs would go more easily. So I just wondered if you could say something in general, right? This doesn't detract from your work. You're doing it for refinement types, but what can we say about the trade-offs between using index types and refinement types?
Well, for me, index types aren't really distinguished from refinement types. So like dependent ML, while it's called dependent ML, it's really a refinement type system, and it uses indices. Sorry, I'm trying to think of how to answer this question. Sorry, could you maybe reiterate the question, like the trade-offs between, are you talking about dependent types or?
Well, right. Consider
versus refinement types, or?
Which is
right.
what you call bad way of doing it. And then you could also do it as a refinement type, right? Just the type vector of n is there exists an x, which is a list of A, such that the length of that list is n. I could do it either way. I've always done it the first way, and I suspect that that works better in AGDA. But maybe I'm wrong. Maybe your answer is to say, no, the other way works better in AGDA. You should try it.
Well, I think, yeah, you'd have to try it. I think you'd have to add that to the AGDA implementation or something. I'm not sure.
Okay,
how that would look like.
We don't know what the trade-off is. There may be interesting ones.
Right.
Yeah, go ahead.
Hi, this is Neel. So let me just answer Phil's question. So Bob Atke and Patty Johan, like some years ago, wrote a paper where they showed that when you have like one of these structurally recursive refinements, you could automatically transform between indexed and sort of the subset style. And right now in AGDA, it's better to use the indexed version, but like, a better AGDA is one where you could switch automatically between the two, and you don't need to rewrite your standard list library for vectors and every possible refinement.
Thanks. Yeah, that would have been my answer if I were more awake.
All right. I think we have time for maybe one more question. No? All right. So if you do have more questions, as you've seen, Neel is here and is one of the co-authors. But otherwise, thanks.
Yeah, thank you.